Um, Please confirm once if my screen is visible, if
Yes,
you can all see my screen.
yes.
Okay, thank you. Um, so it's already 11:45, so I'll start. Yeah. So good morning, everyone. Welcome to the live session on UAV motion planning, minimum snap trajectory planning using the RRT star algorithm. So here's the agenda for today's session. We will begin by understanding the engineering problem, and then we will take a look at the steps that we need to follow to solve that problem. And finally, I will summarize the steps that we will take to reach the solution. And at the end of the session, if time permits, you may ask questions, if any. You may also post your questions in the chat. We will be taking your questions. We will keep a track of the questions, and maybe we will find some way to reach back to you. So in today's session, we will examine how to plan a minimum snap path or trajectory for a multi-rotor UAV from a start pose to a goal pose on a 3D occupancy map using the RRT star algorithm, that is the rapidly exploring random tree star algorithm. So a 3D occupancy map is basically a probabilistic representation of an environment where the space is divided into cubic volumes called voxels. Each voxel stores a probability value indicating the likelihood of it being occupied by an obstacle or being free or being in unknown space. And these maps are created by sensors like LiDAR and are used in applications such as robotics and autonomous driving to understand and navigate complex 3D environments by storing geometric and semantic information. Also, as you can see, our engineering problem is to plan a minimum snap trajectory. So minimum snap is basically a strong heuristic for minimizing control effort in quadrotors. The control inputs for quadrotors, as you know, are the total thrust used for vertical movement and acceleration, and the body moments, which are used to change the vehicle's attitude for horizontal movement. The thrust and moments required to track a planned trajectory can be derived mathematically from the derivatives of position. And it has been shown mathematically that the control effort is basically related to the integral of the square of the snap, which is the fourth derivative of position. So therefore, if we minimize the integral of squared snap, we are basically kind of minimizing the total control effort that is needed for the multi-rotor UAV to track the planned trajectory. So we will do this by using the RRT star algorithm. As you can see on the screen, the first figure shows optimal path planning between two states in a binary occupancy map using the RRT star planner. And the second image shows path planning through a 3D occupancy map using the RRT star planner. So the RRT star algorithm is basically an optimized version of the RRT algorithm, which guarantees that you find a more optimal path as it runs. Both algorithms basically work by building a tree of possible paths through random sampling, but the RRT star algorithm basically includes an extra step of rewiring in order to find shorter connections between the nodes and a better parent for the newly added node, thus resulting in a more cost-effective path over time. So to reiterate, the main steps we will be following in today's session is that we will first set up a 3D occupancy map and define the start and goal poses. We will then plan a path using the RRT star planner, and we will visualize the path. And once we have planned the path, that is, once we have the waypoints, we will fit a minimum snap trajectory or minimum snap path to those waypoints, and we will visualize that path as well. But obviously, just planning a minimum snap path is not enough. That path also needs to be obstacle-free or collision-free. So therefore, in the final step, we will validate that planned minimum snap trajectory to ensure that every state in that path is a valid state. And if that is not the case, if we find that our entire trajectory is not valid, we will modify the waypoints so that the newly generated trajectory is obstacle-free or collision-free. So to be precise, we will try to avoid invalid states by adding intermediate waypoints on the segment between the pair of waypoints for which the trajectory is invalid. So we will insert waypoints iteratively until we get an entirely valid trajectory. So the products that will be required for this session are MATLAB, UAV Toolbox, and Navigation Toolbox. And I will be showing you the code and demonstrating the workflow with the help of a live script. So let's get started with our session. I hope you are all able to see my live script now. It is up on the screen. Please confirm if there is any issue with that. Okay, I got a confirmation. So the live script is up on the screen. So let's first load a 3D occupancy map of a city environment that contains a set of pre-generated obstacles. So I already have a 3D occupancy map of a city environment generated, and I have stored that in a .mat file called uavmapcityblock.mat, which I already have added in the MATLAB path. So let's load that 3D occupancy map to the MATLAB workspace, and let's name it as map data. So if I run this section, you can see that a variable called omap3d has appeared in the right-hand side of my live script. So as you can see, this occupancy map 3D object has a property called free threshold. So this property basically denotes the threshold for considering cells of the map as obstacle-free. This means that probability values below this threshold are considered to be obstacle-free. Similarly, there is another property called occupied threshold, whose value denotes the threshold for considering the cells in that 3D occupancy map as occupied. So basically, probability values above this threshold are considered to be occupied. So in the 3D occupancy maps, there might be cells whose occupancy status is unknown, right? So let's denote these unknown spaces as occupied. So to do this, what we are going to do is, we will have in place this line of code. omap3d.freeThreshold is assigned to be equal to omap3d.occupiedThreshold. So now finally, let's visualize this 3D occupancy map using the MATLAB function called show. So now let's run this section of the live script. So as you can see on the right-hand side pane of my live editor, this occupancy map has appeared. So this is the 3D occupancy map of the city environment that was pre-generated, and it was stored in that .mat file called uavmapcityblog.mat. So we have tweaked some of the properties of this occupancy map 3D object, and finally we are visualizing this occupancy map. So here I want to mention something. In the next section, you can see that there is a try it yourself section. So here you use the pre-generated 3D occupancy map, but you can also randomly generate 3D occupancy maps with the desired dimensions and the desired number of obstacles. So let us go through the entire path planning workflow first with this pre-generated 3D occupancy map, which you just visualized. Then for your own practice, you can later on maybe come back to this section of the live script and you can generate random 3D occupancy maps and see how the path planning workflow works for those randomly generated maps. So let's continue to the second step. So let's now select an unoccupied position in the 3D occupancy map as start pose, and similarly an unoccupied position as the goal pose for the trajectory that the UAV is supposed to follow. So as you know, the complete pose vector of an UAV is defined by the position of the UAV with respect to the scenario's frame of reference, this position X, Y, and Z, and by the parts of the quaternion number, which specifies the orientation of the UAV with respect to the scenario's reference frame. That is QW, QX, QY, and QZ. So let's specify the start pose and goal pose. So I have the start pose and goal pose in place. So now let's plot these start and end poses on the 3D occupancy map. And for that, I'm going to use the MATLAB function called scatter3. So let's run this section. Excuse me. Yes. So like you can see, now the start pose and goal pose have been marked on the 3D occupancy map, and you can see that on the right side of my live editor. So now you are ready to start planning the path of the UAV using the RRT star algorithm. So like I already mentioned, RRT star is a tree-based motion planner which builds a search tree incrementally from random samples of a given state space. The tree eventually spans the search space and it connects the start state with the goal state. So first we have to define the state space. To define the state space, we will use the state space SE3 object, which defines the state space using the position of the UAV in meters and the orientation of the UAV as a quaternion. So in this step, let us first create a state space SE3 object. Yeah. So like you can see, we have also defined a 7x2 matrix that specifies the position and orientation boundaries for the quad rotor. So since the orientation boundaries are optional, I have set the orientation boundaries to INF, that is infinity. So these values in this 7x2 matrix basically specify the state bounds property of this state space SE3 object. So let me run this section. So as you can see in the output pane of my live editor, the state bounds property of this state space SE3 object is basically this 7x2 matrix where you have defined the position and orientation boundaries. Now, while planning the UAV motion, it is also crucial to ensure that it does not pass through occupied locations on the map, right? A motion between two states in the state space is valid only if all the intermediate states are valid. So for that, you can use the MATLAB object called Validator Occupancy Map 3D, which basically interprets the obstacle-free map locations as valid states, whereas the occupied or unknown map locations are interpreted to be invalid states. So basically, this Validator Occupancy Map 3D object interprets a state to be invalid if the corresponding position that is specified by the XYZ location on the map is occupied. So in this step, let's create a validator occupancy map 3D object. So if I run this section, you will see that I have created a validator occupancy map 3D object, and I have stored that in a variable called SV. So basically, this object takes the state space SE3 object, which you have stored in the variable called SS. It takes that object as the first input argument, and it takes the 3D occupancy map as its second input argument, and then it checks the validity of the state space. So as you can see, there is an object property called validation distance, which is by default set to infinity. So this validation distance property is basically the interval for sampling between the states and checking state validity. That is, after what sampling time the states will be sampled and the state validity will be checked by this object. So let us set this property to 0.1. Okay, so let's run the section again. Okay. So now, you have already understood by now that the UAV motion planning or path planning problem is basically a geometric planning problem, right? That requires that any two random states drawn from the state space can be connected. Like, how can we connect any two random states drawn from the state space? Basically, that is what is meant by the UAV path planning problem or UAV motion planning problem. And also that path needs to be a valid path. It needs to be obstacle-free or collision-free. So RRT star is such an algorithm which is used to solve these geometric planning problems. The RRT star algorithm converges to an optimal solution in terms of the state space distance. So we can use the function called planner RRT star, MATLAB function called planner RRT star, to create an asymptotically optimal RRT planner. So let's create that. So this function basically takes the state space object, that is SS, and the state validator object, which you have stored in the variable SV, as the two input arguments, and then it creates a planner RRT star object. And we have stored this object in the variable called planner. So let me run this section. So as you can see, this planner RRT star object has been created, which has the state space as SS and the state validator as SV. Now, you can see that this planner RRT star object has several properties. So let us set the values of some of the properties of this object. So setting the values of these properties, like max connection distance, goal bias, max iterations, max num tree nodes, continue after goal reached. These are all the properties of this planner RRT star object. If you want to know more about each of these individual properties, you can definitely visit the doc pages, the MathWorks documentation pages for more details on this. So finally, we are now ready to execute the RRT star-based path planning in 3D space to obtain the waypoints so that the planner finds a flight path that is collision-free and suitable for the quadrotor. The MATLAB function plan basically takes the planner RRT star object, which you have stored in the variable called planner. It takes the start pose and goal pose that you have already defined. It takes these 3 input arguments and it returns a nav path object, which contains information about the planned path. So let's put that line of code in place. So this MATLAB function called plan, as you can see, it takes the planner RRT star object, which is present in the variable called planner. It takes the start pose and goal pose, and in return, it gives us a nav path object that contains information about the planned path. So we have stored that planned path in a variable called path. So let me run this again. So as you can see, this nav path object has been created and we have stored this object in a variable called path. So as you can see, this nav path object has 4 main properties. The state space property basically defines the state space for the path, and each state in the path is basically a sample from the specified state space, which is state space SE3 in our case. Then there is the states property, which is defined as a matrix. It denotes the states of the path. So as you can see, it is a 7 cross 7 matrix. So the number of rows in the matrix is basically the number of states in the path. And the number of columns in the matrix is the dimension of each state. So like I already mentioned before, that each state in the state space defined by the state space SE3 object has 7 state variables. And that is why, as you can see, the states matrix has 7 columns. The num states property basically denotes the number of state samples in the path. So this is the same as the number of rows in the states matrix. So as you can see, since the states matrix is 7 by 7, so num states is also 7. So basically there are 7 states in the planned path. And the max num states property denotes the maximum number of state samples that are allowed in the path. So if the value of this property is set to infinity, as it is by default, the path basically becomes explicitly resizable. So now that we have planned the path, let's visualize it. So to do that, we can use the plot3 function. Yeah. So let's visualize the path that we have planned. So if you can see the output pane of my live editor, the planned path has appeared. So this path, as you can see, it connects the start pose with the end pose, with the goal pose. But now, the question is whether it is the minimum snap path. The path has been planned with the RRT star, but whether this is the minimum snap trajectory or the minimum control effort path. So like you can see, this original planned path has some very sharp corners, right? While navigating towards the goal. So we will try to generate a smoother trajectory by fitting the obtained waypoints to the minimum snap trajectory. And how will we obtain that minimum snap trajectory? For that, we will be using a MATLAB function called min-snap polytraj. there is a MATLAB function called min_snap_polytraj, which will help us to generate the minimum snap trajectory. And we will try to generate a smoother trajectory by fitting the obtained waypoints to that minimum snap trajectory. So the first step is to extract the waypoints. So like I already mentioned, just give me a second. Yes. So the first step is to extract the waypoints. That is the matrix of state samples, which are represented by the state's property of that object named path. Like you saw here, like I mentioned, the state's property of the object named path. So we have to extract the waypoints from that. So let's store the waypoints in a variable called waypoints. And let's also store the number of waypoints over here. And let's run the section. So now, in order to generate the minimum snap polynomial trajectory through the optimized set of waypoints in the path, the MATLAB function min_snap_polytraj takes a few input arguments. So basically, this MATLAB function takes the set of waypoints. It also takes the corresponding time points and the desired number of samples in the output trajectory. So the MATLAB function min_snap_polytraj basically takes these three input arguments: the set of waypoints, the corresponding time points, and the desired number of samples in the output trajectory. And then the function returns the positions, velocities, accelerations, jerks, and snaps at the given number of samples. So in this step, let's first generate the time points corresponding to the set of waypoints. And let us also specify the number of samples that we desire in the output trajectory. So like I showed you in the earlier step, that we have now extracted the waypoints from the object named path, but we do not yet have the time points corresponding to those waypoints. And we also have not defined the number of samples desired in the output trajectory. So let's do that. So let's run this section. I will try to increase the font size. Please confirm if now it is fine. I have increased the font size by a bit. Okay, I hope it's fine now. Yeah, so like you can see, I have assumed that the UAV speed is like 3 meters per second, and I am calculating the time taken by the UAV to reach each waypoint. So that way, what I am basically doing is I am computing the time point corresponding to each of my waypoints. And I have specified the desired number of samples in the output trajectory as 100, right? So now I am finally ready to use the MATLAB function called min_snap_polytraj so that I can generate the minimum snap polynomial trajectory through the optimized set of waypoints. So let's do that. So as you can see, apart from the waypoints, time points, and the num samples input arguments, I have also specified a few more input arguments, like the min segment time argument has been set to 4. The max segment time argument has been set to 20. the time allocation argument has been set to true. So what does this time allocation argument do? It basically allows us to optimize a combination of snap and the total segment time cost, because we are trying to minimize the snap, right? But at the same time, the trajectory has to be the optimal trajectory. So basically, we have to optimize the combination of snap and total segment time cost. So basically, that is what we are doing by setting this time allocation input argument to true. And the time wait argument has been set to 100, which basically denotes the wait for time allocation. And what do I want from this trajectory? I just want the positions. So basically, this function returns positions, velocities, accelerations, jerks, as well as snaps at the given number of samples. However, because we are focused only on path planning, so we are only concerned with the positions corresponding to the waypoints. So we have stored the returned positions in a variable called positions, right? So now we can visualize the minimum snap trajectory. So we will again use the plot3 function to plot the waypoints, as well as to visualize the positions that produce the minimum snap trajectory. So as you know, the waypoints are nothing but the set of waypoints or the set of states, the set of state samples that are stored in the states property of the object called path. So we have extracted the set of waypoints, and here are the positions that produce the minimum snap trajectory. So let's run this section. So as you can see, an image appeared on the right-hand side on the output pane of my live editor. So this is the minimum snap flight trajectory that has been produced. But if you observe closely, if you observe this figure closely, you will see that the minimum snap flight trajectory has been generated. But is this trajectory a valid one? This trajectory has some invalid states, which are not obstacle-free. As you can see, this yellow path, which is the minimum snap flight trajectory that has been generated, it passes through one of the buildings. A part of that trajectory passes through one of the obstacles in the 3D occupancy map. So you must modify the waypoints so that the generated trajectory is obstacle-free or collision-free. So in order to avoid invalid states, we can add intermediate waypoints on the segment between the pair of waypoints for which the trajectory is invalid. So to do this, we have to write some code. So as you can see in this step, most of the code is written for you. This code basically checks if the trajectory is valid. That is, it checks the validity of the states along the path or along the trajectory. And as you can see, this code uses a helper function called example helper map states to path segments. And this helper function is provided at the end of the live script. So what this helper function does is it basically maps the states along the path to the corresponding waypoint segments. And it identifies the segments for the invalid states. It identifies the waypoint segment which contains that invalid state. So because now we know that, yes, the minimum snap trajectory that has been generated, it does contain an invalid state. So let's compute an intermediate waypoint along that invalid waypoint segment. So like you have already seen, each waypoint or sample state vector has 7 states, the X, Y, and Z positions, which specify the position of the UAV, and the 4 parts of the quaternion that specify the orientation of the UAV. So let's calculate the X, Y, and Z positions of the midpoint of the invalid segment. So like I already mentioned, that code has already been written for you for identifying the invalid segment. So the invalid segment has already been identified. So now I'm trying to find the X, Y, and Z positions of the midpoint of that invalid segment. So similarly, we can use spherical interpolation to calculate the quaternion that is associated with the midpoint of that invalid segment. So once that is done, so this way we can completely define the intermediate waypoint. We have the XYZ positions of the midpoint, and we also have the quaternion that is associated with the midpoint of that invalid segment. So once that intermediate waypoint is computed, so let's just define the complete set of waypoints. So once that is done, so now you will again need to compute the minimum snap trajectory in the same way using the min snap polytrach function. So basically, you identified that there is an invalid segment in the previously generated minimum snap trajectory. All the states along that trajectory are not obstacle-free, are not valid. So what you did is that you identified that invalid segment along that minimum snap trajectory, and you introduced an intermediate waypoint on that invalid segment. So once you have the modified set of waypoints, the new set of waypoints, so now we are again going to calculate the minimum snap trajectory in the same way using the min snap polytrach function. So once that is done, now we are again ready to visualize the minimum snap trajectory. So we have to see that if the new minimum snap trajectory is a valid one. So we will again plot the waypoints. We will plot the initial trajectory, which is the previously generated minimum snap trajectory that was initially generated. And we will also plot the updated trajectory, the final valid trajectory. So let me first run this section where we have computed our new or valid minimum snap trajectory. And now let us visualize. So as you can see, I can just open it up in a bigger figure for you, if that helps. So as you can see, you have the start pose and the goal pose, which are denoted by the red and green dots respectively. The green path that you can see, which has those sharp corners, that is the initial planned path, the original planned path which you planned using the RRT star algorithm. Those are basically the waypoints, the optimized set of waypoints which were given to you by the RRT star algorithm. Then you planned the minimum snap trajectory using the min snap polytrach function. Basically, you fitted those set of waypoints to a minimum snap trajectory. But that initial trajectory which was generated, which is denoted by the yellow color, the yellow path in the figure, that was not a valid minimum snap path because it was passing through an obstacle. It was passing through a building. So all the states along that initially planned minimum snap trajectory were not valid. Therefore, you identified the invalid waypoint segment, and you introduced another intermediate waypoint on that invalid segment, and then you again computed a minimum snap trajectory. And now, as you can see by the blue line, the blue path, that is your final valid minimum snap trajectory. And as you can see, there is a bend in that blue line, which shows that it does not pass through the obstacle. So that blue path, which is the final minimum snap trajectory path, that is an obstacle-free or collision-free path connecting the start pose to the goal pose. So this was our objective, right? To plan an obstacle-free or collision-free minimum snap trajectory for our UAV. So now you have seen how you can use a pre-generated 3D occupancy map. And I also said that we have a section in this live script where we have already provided you the code for generating random 3D occupancy maps. As you can see in this try it yourself section, we have already provided this code for creating random 3D occupancy maps. This code is currently commented out. But if you want to try out the same path planning workflow with a randomly generated 3D occupancy map, you can just comment out the code in this section, and you can uncomment the code in this section. You can enter your desired map width, desired map length. You can also enter the desired number of obstacles that you want in that 3D occupancy map, and you can randomly generate a 3D occupancy map, and you can try out the entire path planning workflow with a randomly generated 3D occupancy map. So, but there can be scenarios where you do not have a ready-made 3D occupancy map, right? So more often than not, you will not be provided with a ready-made 3D occupancy map. What you will have is a real-world environment. Say, for example, an apartment complex where there are buildings, there is a generator room, a security room, a swimming pool. You will have a real-world environment like that. And maybe your goal of motion planning will be something like you have to plan the path of an UAV within that apartment complex such that it will drop off packages that are delivered at the gate to a desired rooftop location within the complex, right? So maybe, say, suppose you have a real world environment from where you have created a UAV scenario using the UAV Scenario Designer app or using a code workflow. You have created a UAV scenario of a real-world environment, such as the apartment complex. And like I mentioned, it has several obstacles. It has a swimming pool, it has these buildings, it has a security room, a generator room, and things like that. So in such cases, what you need to do is that you first need to map the environment into a 3D occupancy map. So before you can even start executing the motion planning using RRT star algorithm, you have to first map the environment into a 3D occupancy map. And in order to map the environment into a 3D occupancy map, you have to use an UAV equipped with a sensor like a LiDAR sensor, and you have to make the UAV follow a specified trajectory through the environment. And you have to use the knowledge of the position of the UAV and the point clouds obtained at those corresponding locations from the LiDAR sensor to build the 3D map of the environment. And for this mapping flight, for this environment mapping flight, we can assume that the pose of the UAV is completely known throughout the mapping flight. This is also known as mapping with known poses. So now, once the environment is mapped into a 3D occupancy map, then you can use that map to plan a desired path for a package dropping UAV. Like you can see in the fourth image, if you want to plan a path for a UAV that will drop a package that has been delivered at the gate to a desired rooftop location within the same apartment complex, you can plan that path for some other UAV. But first, you have to use an UAV equipped with a LiDAR sensor, and you have to use the knowledge of the UAV position and the point clouds obtained at the corresponding locations to first build the 3D occupancy map of the environment, right? So let's take a look at how to do that. So to save time, because we have time constraints, we have already created the UAV scenario of an apartment complex. We don't need to create the scenario right now from scratch. So let us load the UAV scenario. I've already created the scenario of that apartment complex that I showed you, and I have stored it in this .mat file called UAV scenario.mat. So let's first load the file and let's visualize this UAV scenario using the show 3D function. So let me run this section. So as you can see, this is the same scenario that I showed you, the UAV scenario. So now, as I told you, as I mentioned, you have to first use an UAV equipped with a LiDAR sensor to map this environment, right? So that UAV, which will carry out the mapping flight, the UAV which you are using for the mapping flight, that UAV also needs a trajectory. That UAV needs a set of waypoints and a planned trajectory so that the UAV can fly through that trajectory or fly through those waypoints and map this environment into a 3D occupancy map, right? So let's plot the waypoints and trajectory for the environment mapping flight. So first, let me put the sampling times and let me compute the lookup poses along the trajectory at the specified sample times. So these things have been covered in our previous live session also that we conducted for this particular course. Like this particular part, plotting waypoints and plotting trajectory for UAV scenario has been covered in the previous live session. So I will not go into the details of this. So I'm just plotting the waypoints and trajectory for the environment mapping flight of the UAV. So let me run the section. So as you can see here, I'll show in a figure. So this is the environment mapping flight trajectory. So as you can see, this red dot here, this red object is the UAV, the multi-rotor UAV. And the multi-rotor UAV is going to fly through this set of waypoints. The green line is the set of waypoints. And the blue line basically is the trajectory through that set of waypoints. So this multi-rotor UAV, which is equipped with a LiDAR sensor, is going to pass through this trajectory, is going to fly along this trajectory or along this set of waypoints in order to map this scenario, in order to map this environment, in order to collect data. The LiDAR will collect data from the environment so that it can finally construct a 3D occupancy map. Hope I am clear. Basically, the LiDAR sensor that is mounted on this UAV platform, which has already been mounted on the UAV platform while creating the UAV scenario itself. So it will collect data from the environment, like I am reiterating. The data is basically a set of points in the 3D coordinate system, right? So these points basically represent the X, Y, and Z geometric coordinates for samples on a surface or samples of an environment. So like in this environment, you can see there are buildings, there is a base like the floor, there is a swimming pool, there are other obstacles also. So basically, the points in the 3D coordinate system are the X, Y, and Z geometric coordinates for the samples in that environment. So in this step, let us create the point cloud data from this set of points in the 3D coordinate system. And for that, we have a MATLAB object named point cloud. This MATLAB object named point cloud is basically an object that helps us to store a 3D point cloud. So let's do that. So we will use the MATLAB object called point cloud. And we will generate the point cloud data from the set of points in the 3D coordinate system. The UAV, which is equipped with the LiDAR sensor, will fly along the set of waypoints, along the planned trajectory, while collecting data from the set of points, and that point cloud data will be generated. For that, we are using the point cloud object in MATLAB. So let's just run this section. And now, the next step is that we have to map this environment into a 3D occupancy map, right? So we have created a 3D occupancy map with a resolution, with a cell resolution of 1. In order to understand more about this occupancy map 3D object, you can refer to the MathWorks documentation page on it. You will understand what are its input arguments, what is its output argument. You can explore more about that. So basically, we have created an occupancy map so that we have a more efficient way of storing the point cloud data. Basically, we are going to store the point cloud data that is collected by the LiDAR sensor in this 3D occupancy map, because that's our objective, that we have to map the environment into a 3D occupancy map. And then we will simulate the environment mapping flight of the UAV within the scenario. So first, before that, we will put some lines of code in place. So we will store the LiDAR sensor readings so first of all, we will get the LiDAR sensor's pose relative to the reference frame. So for this, in this UAV scenario, in this particular UAV scenario, we have used the east-north up reference frame, the ENU reference frame. So first, we will extract the LiDAR sensor's pose with respect to the ENU reference frame, because we need to store the LiDAR sensor readings for each simulation step while removing the invalid points. We have to remove the invalid points, and we have to store the valid sensor readings from the LiDAR sensor for each simulation step. And then we have to, once the point cloud, once the LiDAR point cloud is there, once we have obtained the LiDAR point cloud, we have to insert the point clouds into the 3D occupancy map. And for that, we again have a MATLAB function called insert point cloud, which we will be using right now. So we will process the simulated LiDAR point cloud. So once we obtain the LiDAR point cloud, we will process it. This is basically just some array indexing that we have to store the LiDAR sensor readings into a cell array format for simulation from each step of the simulation. Whatever LiDAR sensor readings we are obtaining, we are storing that into a cell array after removing the invalid points. So basically just processing step. And finally, we will use the MATLAB function called insert point cloud, where this is the main step of storing the LiDAR sensor readings or the LiDAR point cloud data into our occupancy map. So like you can see, we have created a 3D occupancy map, and we have stored that in a variable called map 3D. And like here you can see, I have used the MATLAB function called insert point cloud, and I have passed that map as an input argument. And I have also passed the LiDAR sensor pose and the LiDAR point cloud data as input arguments. So once I run this section, so if you can see, this UAV is flying along the desired trajectory. I hope you all can see how that red colored dot, which is the multi-rotor UAV object, is basically traversing along the specified set of waypoints and like the specified trajectory. It is basically collecting data. The LiDAR sensor, which is mounted on the UAV, is basically collecting data from the environment through this step. It will just take some time. So once it has completed, yes, I can see a question that is the red point UAV. Yes, that red point, that red object which you saw, which was flying through the specified set of waypoints, it was the UAV. So like you can see, the UAV took that mapping flight along the specified trajectory and generated the 3D occupancy map. You can also play it again at a faster rate. Like you can see, the UAV mapped the environment or the scenario into a 3D occupancy map. And finally, you can follow the same procedure, the same path planning workflow using the RRT star algorithm. I have put all this code in place because this code is this code is basically the same kind of code that you saw throughout this session. Throughout this session, I explained you step by step how to specify the thresholds for demarcating the free and occupied cells in the 3D occupancy map. We defined the state space using the state space SE3 object. We defined the state and orientation boundaries of that state space. We validated the state space using the validator occupancy map 3D object. And then we planned our path using RRT star, and we specified some properties of that planner RRT star object so that we can specify those properties like max connection distance or max iterations, or what is going to be the goal bias. If there is a custom goal function that determines that a path will reach the goal only if the distance to the target is within some threshold. So, and then we specified the start and goal poses, and we finally planned the path using the planner RRT star object and the MATLAB function called plan. So that is why, since we have already covered this path planning workflow throughout the session, I have already put this code in place. So if I just run this code, you will be able to see, as you can see, maybe I can show you in a figure. So as you can see, we have achieved our desired path planning, right? So we wanted to plan a path for an UAV so that whatever packages are dropped off at the entrance, at the security room or at the security gate of the apartment complex, that has to be carried to a desired rooftop location within the apartment complex by the UAV. So we started with a real world environment. We started with an apartment complex, which is a real world environment, right? So we saw that how you used an UAV equipped with a LiDAR sensor to first map the environment and to generate this 3D occupancy map out of that environment. And then you used that 3D occupancy map to plan your desired path for any other arbitrary UAV, any other arbitrary package dropping UAV, which will follow the desired path. So this is all I have for today. I have almost come to the end of this session. But before ending, I will just like to summarize everything for you, what we did throughout this session, what all you saw throughout the live script that I demonstrated. So first you started with a 3D occupancy map, a pre-generated 3D occupancy map, and you defined the start and goal poses. Then you planned a path with the RRT star algorithm using 3D straight line connections, and you visualized the path. Then you generated a minimum snap trajectory, like the initial path which you planned with the RRT star algorithm that had very sharp corners. So definitely it was not the minimum control effort path. It was not the minimum snap path. If the quadrotor UAV has to take such sharp turns along the trajectory, it will require a lot of actuator effort. It will require a lot of control effort. So definitely that was not the minimum snap path. So what you did was you generated a smoother trajectory. You generated a minimum snap trajectory through the optimized set of waypoints, and you also visualize the resulting minimum snap trajectory. But unfortunately, the initial minimum snap trajectory that you planned, it was not collision-free, it was not obstacle-free. You saw how a particular segment of that trajectory was passing through an obstacle, through a building. So it was not a valid minimum snap trajectory. So you validated the minimum snap trajectory and you introduced an intermediate waypoint on that invalid segment to ensure that the newly generated minimum snap trajectory is also obstacle-free or collision-free. And once you were done with that path planning workflow, you also saw how to perform path planning of the UAV using RRT star algorithm on a 3D occupancy map, which is not pre-generated. You actually generated that 3D occupancy map by mapping the UAV scenario of a realistic environment, that is an apartment complex, which is a realistic environment. You mapped that UAV scenario or that environment into a 3D occupancy map and then used that 3D occupancy map to perform path planning of a package dropping UAV using RRT star algorithm. So that's what we basically did throughout this session. And that's all I have for today. So maybe you can all ask your questions, if any. Yes, Dat Wu, I got a question. This technique is for autonomous driving, right? Yeah, like this technique is applicable for robotics, for where you want to plan a path for an autonomous robot. It is for autonomous driving, of course. It is for autonomous flying and navigation of drones as well. Like autonomous or like drone autonomy is a very important aspect of drone navigation and control, right? So yes. And it is different from the previous session. You are right. In the previous session, we created our own waypoints. We specified a set of waypoints, we had a trajectory planned, and we wanted the drone to follow those waypoints, to follow that planned trajectory without colliding against any of the obstacles, right? But here we are planning the optimal path. We are not specifying the waypoints. The waypoints are being generated optimally by the RRT star algorithm. That is the optimized set of waypoints which the RRT star algorithm is giving us. And the trajectory also is being planned with the help of the min snap polytraj function so that we get a minimum snap trajectory through that optimized set of waypoints. And the second part of your question, what if we do not have a general map? So like I mentioned that you might not always have a general map. So I already mentioned that you can generate random 3D occupancy maps. You can also begin from scratch, like you can have a real world environment. So for that also, I showed an example how you can map that real world environment into a 3D occupancy map. Yes, you can modify the waypoints instead of RRT algorithm because RRT algorithm gives you the optimized set of waypoints. Sagar, I'm addressing your question. So you can modify the waypoints, but in that case, it will be a generic waypoint following algorithm. For that was covered in the previous live session where we used the waypoint following block. We used the obstacle avoidance block in Simulink. That how you can make the UAV follow a specified set of waypoints while also avoiding the obstacles. So you can also do that. But this particular session was about motion planning or path planning using the RRT star algorithm. Yes, Dadvu, you are absolutely right. The trajectory which is originally generated from RRT is rough at first. It had very sharp corners actually. So that was not the minimum snap trajectory. If the quad rotor has to take such sharp turns, obviously a lot of actuator effort will be needed. So we are smoothing it out with the help of by generating a minimum snap trajectory. So yeah, like we used the MATLAB function called min-snap polytrach, but what basically happens is the splining method to smooth out the trajectory. Yeah, right.
Hi, ma'am. I'm Malay.
Yes,
Hello.
yes, Malay Kumar, yes.
Ma'am, could you share any practical examples like in autonomy? As of now, just if I tell you we were using some hardware like PixelCube and few autopilots. Okay. So
Yes,
like could you share any like practical examples like how this thing like algorithm works over there?
yes. So, like in these live sessions, covering hardware or demonstrating hardware might not be feasible. But yes, like in the SWAYAM NPTEL course page in the discussion forum, if you can see, we regularly share for every week. We share. Resources, MathWorks documentation pages, and other relevant MathWorks resources. Those you will find in the discussion forum in the SWAYAM NPTEL course page. You can check the discussion forum once after some time, maybe. We can
Yeah,
share,
sure.
we
Thank
can
you very
share
much. Yeah.
over there. Yes, we can share some relevant MathWorks resources over there. Yes. Joshi, last week links that you mentioned during previous section. Yes, I think we conducted a previous live session. I think you can contact the TA for this course, or you can get in touch with the NPTEL authorities for the last live sessions recording. So today's document later on, like if needed, today's document can be posted. You can check the announcements section of the NPTEL SWAYAM course page, or you can check the discussion forum of the SWAYAM NPTEL course page. So maybe the link to today's live script and today's relevant documents will be posted in the announcements section of the course page. You can keep an eye over there. So Akash has a question. Why map is not that of real world, rather boxes? No, it's actually a real world. It's not basically boxes. It's a polygon. Like when you work with when you create a UAV scenario using the UAV scenario designer app, or using a code workflow, when you create the UAV scenario, basically every obstacle can be represented in the form of a polygon, right? So not necessary that the polygon has to be of a definite shape. You can refer to the relevant MathWorks documentation pages to explore more about how to represent different shapes of polygons. Basically, you can just define the corner points of a polygon. You can define the height of the polygon. And by defining the corner points, the location, and the height, you can generate any shape of polygon. So you can make any realistic, more complex scenarios. More complex scenarios or more complex kind of obstacles can also be made. And if you explore the UAV scenario designer app or even the code workflow, like you will see that the polygon is not the only type of mesh that you can add to a scenario. We can also add cylindrical meshes. We can also add custom static meshes. You can also customize your static meshes. You can have customized static meshes also, customized shapes also. Yes, Joshi, we will share the document. We will share the documents, but not right now. We will not share the document right now in the chat. We will be posting the document after some time, after the session is over. We will be posting the documents in the SWAYAM NPTEL course page. Please keep an eye in the announcements section of the SWAYAM NPTEL course page or in the discussion forum. You will find the link. Is RRT algorithm applicable for dynamic environments? Yes, RRT algorithm, I think you can use A-star algorithm. For dynamic environments, A-star algorithm is the hybrid A-star planner. That is a better algorithm for dynamic environments. You can do dynamic planning of a binary document. There are MathWorks resources, there are MathWorks documentation pages which show the dynamic planning of a binary grid, of a binary occupancy map using the hybrid A-star. So I will be sharing the links. Some links will also be present in the live script, in today's live script at the end, when we will be sharing the live script in the discussion forum or in the announcement section. You can find those live scripts and some additional MathWorks resources, relevant MathWorks resources, which are relevant to your questions that you all are asking. I will make sure that I post those relevant links in the discussion forum. So keep an eye over there. I don't get your question, Joshi. Why states are more? I mean, like, what is your question exactly? Yes, 7 states. 7 states, it's the number of, like, if you are talking about the number of states in each state vector, that is because the state space SE3 object, the state space that we have used in that state space, in that state space, basically, all the pose of the UAV is denoted by XYZ positions and the 4 parts of a quaternion that represent the orientation of the UAV. So that is why each state vector has 7 states, right? And why the number of state samples along the path, that is 7. So that is the optimized set of states that was returned by the RRT star algorithm. The RRT star algorithm, when you applied the RRT star algorithm to your problem, like you wanted an optimal path from the start pose to the goal pose, the path which was planned by the RRT star algorithm, that contained 7 state samples. Now, if you remember, there was also a property, that path object, which was generated by the planner RRT star, that path object also has a property called max num samples. You can put a limit on that. If you define the value of that property as 5, then you will have maximum 5 state samples along the path. Because in my case, that property was set to infinity, because that value was set to infinity. So there, I did not put any particular limit on the number of state samples that can be generated along the path. So whatever optimal number of state samples was returned by the RRT star algorithm, that was 7. I hope I have answered your question, that why there were 7 number of state samples and also why each state vector has 7 states. That is because the UAV pose is specified by those 7 numbers, the XYZ locations and the quaternion, which specifies the UAV orientation. Dynamic environment is like, if your environment is changing, yes, A star is used to determine the optimal path or the shortest path, but your environment might change, right? The dynamic environment is like if the environment itself is changing, if the occupancy map, the binary grid or the binary occupancy map itself is changing, it is dynamic, the positions of the obstacles are changing, that way if it is dynamic, so it will revise its shortest path, it will revise the optimal path. So like if your binary occupancy map, or like say if your occupancy map is in a certain state, like then a shortest path will be a certain path will be a shortest path. But now if within that environment, the positions of obstacles are changing, if the setup of that grid itself, if the setup of that map itself is changing, maybe that path will not remain the shortest path. Maybe the shortest path will be something else. So the A-star algorithm can automatically revise that path again. Can again find out, can compute the new shortest path. Okay. So I think I will stop sharing my screen. And if there are no more questions, we can end the session.
Thank you. Thank you so much.
Thank you. Thank you all for being patient. Thank you all for attending the session. I hope it was beneficial for you. And keep an eye on the discussion forum and announcement section of the SWAYAM NPTEL course page. I will be posting some relevant MathWorks resources and documentation pages, like links to relevant MathWorks resources relevant to the questions that you have all asked. I will be posting those, and the session resources will also be most probably posted there. So keep an eye on the SWAYAM NPTEL course page. Thank you. Thanks, Mayur. Thanks, Sagar, Yash, Malay Kumar, Akash, Pratik. Thank you. So I'm ending the session.